All right, we're going to get started on 14.3 here. Not sure if you can read it, but that reads partial derivatives. And so basically we're going to look about taking derivatives of these multivariable functions we've been looking at. All right, so here we've got a definition for the partial derivative, and essentially it should look pretty familiar to you compared to the kind of derivatives we were doing before. We've got the limit, we've got the change in the function, and then we've got it, subtracted from one point to the other, and then divided by h. So that's essentially the same sort of thing where we take that step h and we do how it changed. And this partial derivative here is with respect to x. All right, notice that we're only changing the x, not the y one here. And so that's a partial derivative with respect to x. In other words, what we are doing is holding y as a constant. All right, so we're taking it such that y is a constant and seeing how x varies with it. All right, by doing this, what we do is we look on this surface. We're kind of looking at a plane inside that surface. So we're looking along this line right here, and then we're getting a tangent line to the curve in that direction. All right, so we get that intersection of that plane where y equals y naught, where we're taking it, creates that line, and then we're taking a tangent to that line, and it would be in that plane, our tangent line. All right, right here what we have is the partial derivative with respect to y, where this time we would be holding x as a constant and doing the change in y as we take a step h in y, and getting that same sort of thing as h approaches 0. Here, what happens is we're looking in a plane defined by x naught, and we're getting a line tangent to our surface there, but along that line there, and you can see it right there. If we combine both of these together, you can see here that we have the tangent from the slope from the partial derivative with respect to x, and then I should have done that in a different color. We have this one, partial derivative with respect to x, maybe make that a thicker line, partial derivative with respect to x, and then the partial with respect to y right there. And from this picture, you can see that it looks like that would define some sort of tangent plane to the surface at that point. At least here it looks like it. So let's take a look at an example here. What we have is find the partial derivatives. Notice how it's written differently. We had our df, dx's, those were our implicit derivatives, and now we're doing partial with that kind of curvy d, partial f, partial x. And so this one you'd say df, dx. This one you say partial f, partial x, partial like that. So you say partial for that little curvy d instead of saying d. All right, and so here we have this partial derivative of f with respect to x, and you can see there that it's we're going to do that, and then we're also going to do the partial derivative with respect to y at the point 4, -5, and we're given this function x squared plus 3xy plus y minus 1. So to find the partial derivative of x, you essentially are just going to take the derivative but treat y as a constant. And so instead of doing the implicit differentiation, you're just going to do this. You go through, you take x squared, it becomes 2x. You take 3xy and you treat y just like you would the 3, as though it was a constant, and you just take the derivative. So with our implicit differentiation, you would have had to have done, like a derivative of 3x, and then had to have also done the dy dx on there as well. But here we're treating it as a constant, so just derivative of x becomes 1. And then here, derivative of y, well, we're treating it as a constant, so it becomes 0 right there, right? So this derivative becomes 0, and then this constant also becomes 0. Okay, so those are our partial derivatives right there. Don't get all those little marks all over. And then you just get 2x plus 3y for the partial derivative with respect to x. We will also write this as just an f with a sub x down there as a short notation for the partial derivative with respect to x. This one would be partial derivative with respect to y right here. And you're doing the same thing, except this time you're holding, oh, sorry, and I forgot, then you also have to then plug in for -5. So you plug it in for and -5 and get a -7. So for that specific point. All right. So we'll do the partial derivative with respect to y now. So you're going to hold x as a constant. That means this is going to go to 0. This is just going to go to 3x. This is going to go to 1. That's going to go to 0. And you get 3x plus 1. You plug it in, and you get the slope of the tangent line at that point. You plug in your points, and you get that negative 13. Okay, so nothing too horribly complicated there as far as actually doing them, but there you go. Here, excuse me, another little example is find the partial derivative with respect to y as a function if f of xy is y sine of xy. So treat x as a constant and f as a product and just go through and do it. So you're going to treat it as a constant and do the regular old product rule. So you see what we're doing? We're getting the derivative of the second times the first plus the first, or the second times the derivative of the first. Okay, so that's all that's happening there. We're just going through and doing the product rule, and you just take it. You treat the x as a constant. It ends up when you do chain rule getting pulled out front here, and you just treat it as though it was like the number 2 or something like that. Here's one, find f sub x, and so partial derivative with respect to x and the partial derivative with respect to y for this one. So I'm going to leave that one for you to go ahead and try. You've seen 2 examples of doing it. So just remember, this f sub x means partial f partial x, and then this f sub y is partial f with respect to partial y, like that. So partial f partial y. So that's the 2 things that you need to calculate there. So go ahead and give that one a try. After you do that one, here is another one, is to find d partial z partial x in the equation here. It defines z as a function of the 2 independent variables. So you're going to do this one. I'm going to leave this one for you again to try, just like you would if this was a function f in there. So go through and actually do the derivative with respect to that. Okay, so give that one a try as well, and then take a look back in the notes if you need to actually see it finished up. Excuse me. The plane x equals 1 is going to intersect this paraboloid that's z equals x squared plus y squared into a parabola. Find the slope of the line tangent to it at that point. And so what you would do here is essentially take a partial derivative. Now, we're treating this plane that's defined by a constant value of x. So we would essentially just take that constant value of x, do that partial derivative with respect to y, and it would just give it to us right there on it, and we'd get the tangent line there for it. Okay? So hopefully that kind of makes sense to you. That's what we're doing. We're slicing it right there and then getting that tangent line right there that's tangent to it at that point, or tangent to that curve from that intersection of that plane. All right. Functions of more than 2 variables here. If x, y, and z are independent variables, and we have this function f of x, y, z equals x sine of y plus 3z, then partial f partial z equals the partial derivative of this, and you can go through and just do partial derivatives just as you were before. So just another example there of doing that. We can just kind of extend this out. It's x, y, z. But again, if you're doing it with respect to z, you treat x and y as constants. So the same idea extends out to these higher tuple ones. Here we have a resistor, and we have this resistance, and we would want to do the partial derivative here with respect to R2. So they're saying with respect to this. And so we have it in this weird form. And so what you can do is, oops, what did I do? Oh, I clicked the wrong one, sorry. So what we can do here is just go through and actually make this a function of R. So this would be R equals, and then what I can do is make these all have the same denominator, right? So this one has to be R, so actually let me do it this way. Let me show you first. So 1 over R has to equal, and then we have to have R1, R2, R3 in the denominator. That's our common denominator for each of them. This first one is R2, R3. The middle one would be R1, R3, and the last one would be R1, R2. And so then I can just solve this for R, which is R1, R2, R3 over R2 R3 plus R1 R3 plus R1 R2. And then at that point, you need to go through and do the partial derivative with respect to R. Again, treating R1 and R3. Whoa, what happened? Treating R1, I don't know why that happened. Treating R1 and R3 as constants, but treating R2, all the R2s as variables, and then you can go through and figure out how it's changing as you change that R2, holding the others constant essentially. All right, partial derivatives and continuity. Here we're looking for an example. You can find the limit as f of x approaches there along the line y equals x, and all this kind of stuff. So what we're looking at this graph is we want to see if f is continuous at the origin, and by that, we use our partial derivatives to look at it in each direction. So if f of xy equals this, x cosine y plus y e to the x, we can find the second order derivatives here. We can actually do higher ones. Here you can see that we could do two partial derivatives with respect to x, or we could do partial derivative with respect to y and then with respect to x, and just go through like that, and then do two partial derivatives with respect to y, or one with respect to x and then with respect to y, and then you can see this here. You would essentially do, like for this one, you would do the partial derivative with respect to x first, and then you'd come down here and do a partial derivative with respect to y after that on your result. And that's what would give you this one here, okay? And then over here, you can do the same thing, just in reversed order, and not necessarily getting the same result with both of them. So you can see the 4 different results there, and you can see here, though, we're getting the same result for, it didn't matter which order we actually did them in. So take a look at this. We have a mixed derivative theorem. If f of xy and its partial derivatives f sub x, fy, and fxy and fyx are defined throughout an open region containing a point AB and are all continuous at AB, then, here we have our continuity here, then those two partial derivatives will actually be equal to each other, okay? And go through like that. So this one here, you can see we have another example here. And again, I want to leave this one for you to try, because best thing to do with these partial derivatives is just practice them. But what you're going to want to do, and I would recommend you try it both ways. Try calculating partial w, partial y, and then do partial x of that, right? Try doing it this way, and then do it the other way. Try doing partial x, right? Then doing partial y of that partial x, like that. So try doing it both ways and see what answers you get, and see if it mixes with this theorem. Okay, here example 11, I actually went ahead and did this one out because it was kind of long. So you can take a look at that here if you want to pause it and take a look as I went through and did the different partial derivatives. Okay. Next, theorem 3, the increment theorem for functions of two variables. Suppose that the first partial derivative of f of xy are defined throughout an open region R containing the point x0, y0, and that f, or partial derivative with respect to x and partial derivative with respect to y, are continuous at x0, y0. Then we have this change here. We can say that we have some delta z that will equal a step in it, f, where we step a delta x in x and a delta y in y, minus our original point. And the value of f that results from moving from x0 to another point, x plus the delta x, y0 plus the delta y in R, satisfies an equation of the form, then, delta z equals our original function with the partial derivative evaluated at x0, y0 times that step in delta x, plus our partial derivative in y, which kind of tells us how steep of a thing we're doing, times that step in y, plus some epsilon times the delta x plus the epsilon times the delta 2, a different epsilon 2, in which each epsilon 1 and epsilon 2 go to 0 as delta x and delta y will go to 0. All right, so let's take a look at another definition here. A function z equals f of x, y is differentiable at x naught, y naught if the partial derivative evaluated at x naught, y naught and the partial derivative at y evaluated at x naught, y naught exist and delta z satisfies an equation of the form, and then we have that same form here, tells us this is differentiable, so if it matches what we were saying we could do over here, then we've got something that is differentiable, in which each of the epsilon 1 and epsilon 2 go to 0 as delta x and delta y go to 0. We call f differentiable if it is differentiable at every point in the domain. All right, so there's how we can see if we're differentiable. It's basically saying if we can take the derivative, we can. All right. Corollary of that theorem 3 is if the partial derivatives, one with respect to x and one with respect to y, of a function f of xy are continuous throughout an open region R, then f is differentiable at every point of R. All right, so if our partial derivatives are continuous throughout the open region, then it's differentiable at every point inside of there. Here, a lot of theorems in a row here, I know, a lot of stuff in a row, but differentiability implies continuity. If a function is differentiable at x naught, y naught, then it is continuous there. All right, so continuity or differentiability is going to imply continuity for us. All right, and that's it for that section. So that ends it for us. Go back, try those ones I left blank for you to try, see how you do, and then, let me know if you have any questions. All right, that's it.